I don't know which ones you want to do.
Mm,
Have you looked at some of them already?
No, I haven't, but I'm looking, I've got on my laptop now.
Okay.
Um, we could talk about number one, because sometimes those confuse me.
Okay.
Actually, the majority of the time.
All right, let's see if I can make sense of this thing. Identify the reagent needed to complete the following reaction scheme. All right. So if we look at the product, let's look at it this way. Let's say the product is this cyclopropyl in here. And then ding, oxygen there, right?
Yeah.
Ding here. And
Double bond.
double bond there. Okay, if we're gonna form that from that precursor, then where does the bond that needs to form the replacement needs to form here, right? Right there. Because we're working from
Yeah, a couple more and a bromine.
Yeah. And then what do we have left over? Well, we have 1, 2, 3 carbons. 3 carbons. 1, 1, 2, 3, like that. Now, do we have an oxygen here?
Yeah.
Maybe like that? I don't know. But if we did, if that wouldn't work, right? Because if this is going to be the electrophile, right, we got to form a bond here. Then this would have to be the nucleophile. Right? It would have to be like that so that we could attack that and this would
break
leave.
that off. Yeah.
And that would leave.
Okay.
So in order to do that, we would need let's see. I guess it was BD. Right, 1, 2, 3. D, CH2, CH, and CH2, right?
Yeah. But
And
where's
then
it?
oxygen,
The potassium.
and then a potassium. So this would be plus, and this would be minus. So this would be that end. And this, by convention, this carbon has an oxygen on it. It has hydrogen here, carbon here, hydrogen there, which means attached to this carbon with a 2 hydrogens here. That means in order to complete the octet, it has to have a double bond there. So this is drawn correctly. And that would be the right compound.
So if I were just to be looking at this, I would probably choose A over D. Like I know I would choose A over D.
Oh, A wouldn't work because it's still got the hydrogen attached.
Okay, so we gotta get rid of the hydrogen.
Yeah, you need
Okay.
you need that anion as a nucleophile.
Okay.
Yeah, that's the trick. That's the one that'll catch students. All right.
What about 6?
Six, 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 six. Here we go. What reagent would be the best choice to complete the following reaction? Okay. So let's see, that's a weird one. Got a cyclohexanol here first. And then we have fused ring on top with an oxygen. Okay.
That would be oxygen, correct? Or
Uh,
are we just like putting that there? It just happens to be there.
Yeah, I wouldn't call it oxirain. It's going to be a complicated name. That's why we don't have a name for it. And we want to end up with the ring does open though. And we still got this one here. And then we have the bromine, is it? Yeah, bromine. And we have the
OH.
OH. Okay. So what we need to do is okay. Where's the ring gonna open? We want the ring to open here, don't we?
Yeah.
So that gives us the hydroxyl on this side. So if we're going to attack this is the more substituted carbon here. I mean the least substituted carbon here. 1, 2, 3. Oops. This one is completely substituted here. 1, 2, 3, 4. There are no hydrogens there. So we need something that will attack this, and we need to end up with bromine, with a bromide on it. So will this work? Can this work here? That. And then this opens up. Seems like that would work.
So would it be B?
Well, B is,
I'm at C.
I wonder. I think C would attack this side. And the bromide would attack this one, the more substituted one. We saw that earlier, I think, with the difference between using hydrobromic acid versus PBr3. Yeah. Because HBr is going to give us the bromide ion.
So it's E.
Yeah, I think E would work.
Seven looks a little weird to me.
Okay. Let's see. One. That one. Carbonyl. Is this symmetrical? Yeah, it's symmetrical. Okay. We want to end up with. We just want to substitute a chlorine, don't we?
Yeah.
Okay. Hmm. We want to chlorinate an alpha carbon. And it's symmetrical, so actually it doesn't matter which side it attacks. Right? There's no regioselectivity involved there. Both alpha carbons are equivalent. Hmm. You got me. I mean, I see the answer there, but I don't see how it works. It's
Just
a
looking at it, I would think it's either D or E. Is that one of the options or one of the answers?
no.
No.
It needs to. We need a leaving group. So I bet this is going to take place in 2 steps. right, are there any hydrogens here? Yeah, there's a hydrogen there. There's a hydrogen there. So if we come in there with, um, I don't get it.
Well, let's just hope this one ain't in the exam.
Well, I can be sure it's not.
Yeah.
So let me, while I've got it open. See. No, what is it like? There. Make sure I don't use that one. Any others? Are you looking? Are you gonna try to give me another one of those? Yeah.
Number 12.
Okay. What's the major product of the fall? All right, we have that and this. And we're reacting with dilute hydrochloric acid. All right, what's the acid gonna do? Under acidic conditions, I would expect this um, to be protonated. I would expect this to be protonated. Okay. No. Well, maybe that's true. Maybe it would. Yeah. What's the other possibility? The other possibility is for that chloride to do something. So could the chloride attack this carbon because of that oxygen? I'll tell you what. Let's check. It's probably chapter 10. Right. Chapter 10. We didn't talk about it today, did we?
I think so.
No. Here we go. Oh, is this a Williamson? No, because there's no bromide there. There's no chloride. There's no halogen there. It's not a Williamson. I don't know. Here we go. Okay. All right, here's what it says happens. Proton transfer first. So this was correct. I was on the right track here. Now it's positive. So we get a proton transfer first. And then another one of these attacks that carbon, right? No. Yeah, it attacks the carbon. This is our leaving group. So that gives us water. And this forms a bond here. So now what we end up with is that. So the key to this one is that under acidic conditions, we protonate that group, makes it a good leaving group. Then this carbon is slightly deficient. And that nucleophile attacks it right there. So that means A. A would be the product.
Would be 13.
All right, which of the following synthetic steps would be classified as a functional group conversion? Functional group conversion. All right. Well, the first one is a ring opening. The second one, B, is carbon skeleton chain lengthening. C is a ring closure. Oh, it's a ring closure and it's a carbon skeleton change. So B and C are both carbon skeletons. See? So that's 1, 2 carbons out here at first and 1, 2, 3 now. So we've added that carbon in here. Okay, how about D? A functional group conversion. D is a substitution, but it's a different functional group, isn't it? Oh, I see. It's just a substitution. It's not actually changing the functional group. We're substituting a functional group. A conversion changes. So we're going from a bromide to you know what? I think this is a problem of definition. So let me look it up. Let's see, functional group transformations, functional group conversions. Defined. 551. Here we go. Reactions that form and or break carbon-carbon sigma bonds alter the carbon skeleton, whereas functional group conversions do not alter the carbon skeleton. Section 10.3. They give us examples, I guess. Okay. Here we go. I'm getting warm. This comes under cataloging reactions. Okay. Functional group transformations or conversions simply transform one functional group into another. They do so by leaving alone the carbon skeleton. Okay. Okay. So D is not a functional group conversion because we're adding a carbon to the skeleton. That's what threw me. I said, wait a minute, we're changing a cyanide and a bromide. No, but we've added a carbon bond to it. So D is not a conversion. Right? C is not a conversion. We've changed the carbon skeleton, and B changes the carbon skeleton. A, 1, 2, 1, 2, 3. We changed the carbon skeleton in A also, didn't we? Yeah. Okay. So by process of elimination, E is the only answer. Yeah. E is the right answer. Okay. I learned something new. I'll have to do some heavy editing to this one, this video. There's a lot of dead air.
Let's try. Let's try 21.
What?
It's kind of what we just went over with the carbon skeleton.
Okay. I want to keep track of what we've been doing here. So this one, we did number 1, right?
Yeah.
Did number 1. So I'm gonna highlight that one. And we did 6, was it? 7.
And then we did.
Oh, we did 6 and 7, right?
Yeah. 6, 7, 12, 13. And now
6. Okay, I blacked out 7 because I didn't understand it. And then we did 12.
Yeah.
Yeah, 12. 12. Oops. And 13. Ah. Okay, now we're going to 17, 16, 17, is it?
21.
21, excuse me. 20. Okay. Which of the following steps would result in an alteration of the carbon skeleton? Okay. All right. The first one is not going to, it's just going to open the ring and brominate. So we're going to have a bromohydrin. Excuse me. The second one is, let's see, tertiary butoxide. That's going to form What is that one? Okay, the nucleophile is on the arrow. So it's going to attack the carbon that's attached to the bromine. You know what? It's a strong base. I bet it's going to attack the more substituted, not the carbon, but it's going to extract the hydrogen. But that's not going to change the carbon skeleton. It's going to form probably an alpha beta alkene. Okay. How about C? Let's see. We got a Grignard reagent, and we're going to open up there's that funny compound again. We're going to open up that ring and attach. Yeah, we're going to attach an ethyl group. So C would change the carbon skeleton. Yeah. How about the others? Let's see, sulfhydryl. No, that's just going to substitute for bromine. And the bromine and acetic acid is going to form a bromohydrin. Yeah. So the only one that's going to change the carbon skeleton is C.
Mm, 31 looks pretty difficult.
Okay. Which of the following reactions does a reversal of polarity at a carbon atom take place? Reversal of polarity at a carbon atom. So it's either going from a carbanion to a carbocation or vice versa. All right. Well, let's see. In the first one, that group on the arrow is simply going to be a nucleophile. That's it. It's not going to reverse its polarity. When we add lithium to that bromide in B, the carbon attached to the bromine is a slightly positive first. Then we stick the lithium in there, and that changes the polarity. Yeah, B would change the polarity of the neighboring carbon. It would go from a carbocation to an anion, formal charge. If we use wait a minute. Hold on a second. Okay. the ABCD, I have to see which one applies to what. So the B applies to the one with the bromine and the lithium. And the C applies to, why is that 2 sticking up there?
I don't know. One,
Oh, maybe there are 2 of them.
yeah.
Yeah, there are 2. Right.
Squared.
Right. 2 of them. Yeah, you're right. Okay. So no, that doesn't change the carbon polarity. It just bridges between it just forms a dimer. And the Grignard reagent. Now, the Grignard reagent itself has reversed its polarity to get there, but that's not part of the reaction. Right. The only one that reversed its polarity was B, when we put that lithium in there. And what it doesn't show you is that the bromine is still around. Only the bromine is technically separate from the lithium compound. We went from a non-metal attached to a metal attached, and that change in that's gone blank again. That change in I'm having a Biden moment. Electronegativity. That change in electronegativity caused a change in polarity of the carbon. So B is the best answer for 31. Okay. Oh, 32. Define the term Umpolin. Polarity reversal.
Say, I don't think I.
It's in the text. Yeah.
Is there any ones that you see are like extra difficult just by looking at them?
Yeah, there are a bunch of them that are difficult for me. So if I can't figure it out, I'm definitely not going to use it in the exam. It is for the intent product. Okay, we did one like that already. Relative positioning the heteroatoms. Okay, it's the relative positioning of the heteroatoms. 1, 3. 1, 2, 3. Yeah. Which of the following reaction would not function as an effective protective reagent for an alcohol? You'd have to look at the, for 38, you'd have to look at the handout. Oh. Yeah, okay. I gave that handout to you.
Yeah. The one.
Yeah, for
Big
chapter
sheet.
21.
Yeah.
Chapter 21. Do you have that with you?
No, not with me.
Okay. Let
Well,
me,
actually, let me make sure.
I probably got it in here
So
somewhere.
they usually take all my organic stuff out.
Here we go. Let's see, which would not serve as an effective protectant? PBDMS, we looked at that one just recently. Right? So that would protect the alcohol. Okay. Oh, this is obvious. Okay. TBDMS for the first one. For C, we're forming ether. Right, that protects it. D, we form another ether, protects it. E, we form another ether. So all those ethers protect that group. But B does not. KMNO4 simply forms another carbonyl group. Right, that's easy. Yeah. It's probably why you didn't mention it, right? Ketones are commonly protected from strong nucleophiles. That's the acetal, right? That's one of them we went over. We protected a ketone by forming acetal. Which of the following reactions does not use a selective reagent? This is number 40. Does not use a selective reagent. That one could be trouble. Well, let's see. The tertiary butoxide. Yeah. The tertiary butoxide in A, are you looking at 40?
Mhm.
Okay. It would attack the least substituted terminal yeah, the terminal methyl end and remove a hydrogen. No, no. Or would it attack the carbon? The carbon would be slightly positive, the tertiary butoxide anion. It's a strong base too. So do we have any acidic hydrogens there? No, we don't. Okay, so it would attack the carbon on the bromine. And No, it would attack that. It would attack the hydrogen on the carbon attached to the bromine. Oh, but it can't be selective. Not use a selective reagent. Well, it is selective. The Grignard reagents are always selective. LDA is always selective. Chloride ion. Well, yeah, we could say it's selective. It's going to attack the carbon with the tosyl group on it. How about lithium aluminum hydride? Is it selective? Not use a selective reagent. It would just, let's see, what would it do? Lithium aluminum hydride. That's a Lewis acid base reaction there. All right, I don't like that one anyway. I know what to do with that.
Toss it.
Yeah. Umpolone. Which one? 41. Which one involves umpolone? Which is a reversal. Involves. Well, it won't be number 2 because it's already got a metal on it when we put a copper in there. So that's not it. No, C would not be it.
And wouldn't it be selective? Or what? I mean, does that matter?
That doesn't matter.
Oh.
Not to answer the question. The only one that comes close is D. The only one that comes close is D because you can see the attachment of that triphenyl phosphorus attached to the carbon. It changes the charge on the carbon from well, actually it adds a carbon. Doesn't it? Yeah, it adds a carbon. You know that there's something wrong with that one. Where did that carbon come from? It's not there. That's a bad question.
They're all bad in my book.
Yeah, that one's not worth. That's not a keeper. No, because we stuck a carbon in there, and where did it come from?
Yeah.
Right. All right, let's keep on moving on.
42 is our last one.
Okay, which mechanism step is involved in the following protection? Okay. Bimolecular elimination. We didn't eliminate any. Oh, okay, I see what it's doing. It's like an E2. Bimolecular elimination is an E2. No, we didn't eliminate something. We added something. All right, so we can do away with the eliminations. Is it a nucleophilic? No, if we form a bond with oxygen is the nucleophile, but we're adding an electrophile to it. I think this is a reaction that we haven't studied. It's supposed to be an electrophilic addition. I don't know what to do with that one. Let's go back to some that we haven't looked at yet. Did we skip any that are particularly interesting?
Some of the definitions, which
Yeah, well, the definition shouldn't be a problem, right?
No,
Which of the following solvents would be considered the most green? Number 30.
yeah, that one's pretty easy. Leave that one in there.
Okay.
I'll get that one right.
Which of the following best describes the goal of green chemistry to avoid production and accumulation of hazardous materials? Oh, yeah.
What about 9?
Go back to 9. Back up.
I just have to scroll up instead of going from the bottom.
9. Here we go. Yeah, I wonder why you didn't stop at that one the first time around.
Just scrolling through.
Yeah. We're on the learning curve here, both of us. Identify the reagent needed to complete the following reaction scheme. Okay. So we're adding a methyl group to that, the oxygen on the carboxylic acid. Yep. Okay. So if that's the bond that's being formed, what's the electrophile and what's the nucleophile? The nucleophile would have a deficiency. No, man, it would have an excess electron.
Wouldn't the electrophile be on the hydrogen?
Yeah, I think what it's going to do first.
I'm sorry.
Yeah.
I'm trying to figure it out as you go too.
Oh, okay. Has it been a while since you had
It's been a while since I've
Yeah.
had that, yeah.
Yeah. Let's see. So we can just draw this part of the molecule here. The rest of it is irrelevant. And then what is going to give us this? It's going to form an ester, right? We need a methyl group on that. So what will give us a methyl group, right? If we use, let's work from the bottom. If we use the alkoxies, like the sodium and the potassium compound and this compound, that's going to try to form a bond with the oxygen, not with the carbon. We need something to form a bond with the carbon. So it's either A or B that will form that bond.
But we want to get rid of the hydrogen, so wouldn't it just be A?
Yeah, probably would. I'm not sure how that would work though. Let me take a quick minute and look up esters as a refresher. Ester. Let's see, this is we haven't studied that one. This is in the wrong chapter. Nope. That's not what I did. No. Let me look at it from carboxylic acid side. 1119. Nope. Let's see, that's ooh. That's methyl azide, isn't it? Where did that come from? We ought to have that in our reaction tables. Functional group transformation. Here we go. All right. I had just happened to flip to it. In table 10.1, it's reaction number 9. It's an SN2 reaction. In section 10.9, that's where it's discussed. So let me turn to 10.9 to get a better idea. Oops, that's not it. Here we go. Diazomethane. Ooh, that's the explosive one. Diazomethane. Yeah. Okay. Well. Okay. So here's what it's going to do. According to this, the diazomethane has an electron-rich carbon. And 2 hydrogens. Yeah, 2 hydrogens. An electron-rich carbon. So this one's negative. Okay. And it attacks this hydrogen. This attacks that hydrogen. Extracts that hydrogen. And produces the this. Okay, extracted the proton. Okay, now what that's going to do is go back and attack. Now that this one has an extra hydrogen on it, we've got these 3 hydrogens here. Now it doesn't have negative charge anymore. But this one is still positive. And so now this one attacks that carbon. And then these go over here, and that produces nitrogen gas. Plus the methyl ester. All right. That was a chore.
So it is A though.
Huh? Yeah, it is A. Uh-huh. Diazomethane. Diazomethane. Find any others? Eight's pretty simple. It's simply a
Well, you go over 17,
17,
or did we go over 17?
maybe.
Yeah, we did. No, we didn't, or maybe we just did that. I think we did go over.
No, I don't think we did.
Maybe I was eyeballing it for a little too long.
Yeah. That. $17. Okay, fill in the missing precursor to complete the following. Okay, so this one, we're going backwards. Oh, okay. All right, so we got the product we want to produce is 1, 2, 3, 4, 5. 2, 3, 4, 5. And the methyl group here. And hydroxyl there. Yep. The way it's written, that needs to be our product. Okay, so one of the reactants is this. There. And we need another reactant that will give us this. All right, what we've added here, we've got 1, 2, 3, 4 carbons. And this ring opens to give us that hydroxyl on the number 2 carbon. So it opens this way. 1, 2, 3, 4. 1, 2, 3, 4. Right. So we need to add an ethyl group on it. Yeah, we need to add an ethyl group right here. Like that. Oh, yeah, because this is going to open. That's going to break that bond and open it up. We're going to form a carbon bond. Okay, so what we'll do that. We need, this is going to be positive. We need a negative. We need a negative carbon in order to attack that carbon and form the bond. So which one of those gives us a negative carbon with only an ethyl group, 2 carbons? It looks like E is the only one that would work. Right? That Grignard reagent will make that carbon. CH2, make that carbon, oops, not positive, make that carbon negative. And bromine. And so these here will attack that carbon. I didn't curve my arrow though. And that opens this up. And actually it opens it up to that. So it doesn't directly give you that product because you got to do an acid workup in order to get it. So this is going to be negative here. And then we do an acid workup, say hydrochloric acid probably. Or hydrobromic acid for that matter. And that will form the bond. So E would be our best answer for that one. Right. Let's see. 11, which of the following mechanistic steps is required in the formation of the following ether? Heterolysis. Heterolysis. Ah. Yeah. Actually, it's 2 steps. You form with the acid, you form the a good leaving group, a water leaving group, where that OH is now, OH2, and then that leaves, forming the carbocation, and then another isopropanol comes in and attacks that carbon and forms the ether. Yeah, that's a good one. Yeah, we could do that one. 10. Williamson requires an SN2. Eight's okay. I mean, if it's an SN1 reaction, you have, let's see, 1, 2, 4. If it's an SN1 reaction, then we have to have a leaving group first. So this leaves. And what we have left over is this carbocation. And then, let's see. Oh, excuse me. What am I talking about?
I thought you were going backwards.
I was. I got the wrong precursor. There we go. And HBr, all right, what it does is it protonates, forms that, and then that leaves, and that leaves behind the carbocation. So now the SN1 reaction can take place, and the bromine can attack that, and that forms.
That one makes sense to me.
Yeah. It's nice that they told us it's an SN1. Otherwise, I wouldn't have known to do that first. Well, which of the following should not be included in a synthetic step? Oh, okay, that's simple. In a synthetic step, you don't do mechanisms at all. Reagents, solvents, temperature, time, those are all valid. Mechanisms are not allowed in a synthetic step. Yeah. 16, in comparing synthetic schemes, which of the following is not a consideration? Minimizing overall cost. I guess when you're only talking green, you have to think like a communist. It's always somebody else's money.
Yeah.
But then if you turn capitalist, your green chemistry is tempered by cost.
So long green can either be super expensive or could be, could save money too. at
Yeah.
times. Yeah.
Exactly, right. I don't think you'll have any trouble. How do the overall percent yields of the following linear and convergent syntheses compare?
It's pretty easy.
Yeah. Do that one. This would be 85 to the fourth power, and this would be 85 to the second power. So the convergent synthesis has a higher overall percent yield. That's simple. What starting material should be used to complete the following reaction with highest yield? Something cyanide is going to be highest yield. Okay. We want a cyanide. All right. Well, you want a really good leaving group, but the highest yield will be a single step, I would think. So if you had the bromine, if you had a bromine, which is an excellent leaving group on that carbon, but it's on the backside, then if you had an SN2 attack with the cyanide ion on that carbon, it would, the bromine would leave off the back and the cyanide would be on the front.
So it'd be E.
Yeah, I think E would work the best. Missing precursor needed to synthesize the following molecule. Oh, okay. Well, I'm not so sure that that's the alkanide ion. So that should have a negative, I think. Unless there's a hydrogen there. Okay. So if there's a hydrogen there, I don't know about that. We need, okay, if we're going to break the bond here, it needs 1, 2, 3, 4 carbons. Right? You're not going to do it with butane. You're not going to do it with the epoxide. It's just going to open up.
E makes sense to me because you would, the bromine would leave. So that would
Yeah.
be 4.
1, 2, 3, 4. Yeah. How about 1, 2? Oh, the iodide doesn't have enough carbons on it. Aha. It would probably be a better choice. And you're not going to have the negative because this is going to be slightly negative too. Yeah, E would be the best choice. Not be included in a retro synthetic analysis reagents. Yeah. Which of the following solvents would not be a good choice to use when carrying out the following reaction? Okay. If we did it in methanol, that's a protic solvent. So this alkoxide is simply going to deprotonate the methanol. It's not going to have anything to do with that precursor. It needs to be not be a good choice. Some of those others, of course, E, D, and A are all aprotics. But what about 1, 2, 3, that propanol? If we used propanol, yeah, we could do that, right? We'd have how to name the compounds. sodium propionate. So yeah. So as long as you've got the propanol is common to that sodium compound, right? They share that part. So I don't think that would be a problem. But if you try to use methanol is more acidic than the propanol. Right. That would be the one that I wouldn't use. The methanol. I'm going to brush up on my nomenclature. Generic synthetic scheme. It's a linear synthesis. Yeah. It's not a convergent. I mean, if you multiply all those out, you should get 37%. I'm just identifying the keepers, which the following would not be a reasonable precursor of the following target. Okay. Well, let's see. We've got this a benzyl group on that side with an ether and a isopropyl on that side. All right, so there's an isopropyl, there's a benzyl bromide. There's an isopropyl bromide that could work, and there's a benzyl alcohol. Okay, so if we did the reaction with the A and B, we get that product. If we did the reaction with C and E, we get the same product. But we wouldn't get the product with D. D wouldn't give us anything near what we would get. That's a keeper. Overall percent yield, 5 steps, 90%. That's simple calculation. Keep that one. What's the major product of the following reaction? Ooh, that's kind of hard to read. Is it easier to see if we make it smaller? I'll throw it out. The graphic's not going to work. There's no sense in keeping it.
Yeah, the next one's a little blurred too.
Yeah. At least we can see the reaction conditions. Sodium hydride and tetrahydrofuran. Okay, that's going to extract a proton from the alpha carbon. Extract a proton from the alpha carbon, which would make it a carbocation, and then we attach a methyl group to it. So A would work. Right, we're going to attach that methyl group to this one after we form a carbocation. That's a good one. Keep it from messing up. We looked at almost all of it. Well, that one's obvious. Keep that. What's the relative positioning of the heteroatoms in the following molecule? The heteroatoms. I assume that means oxygen versus the cyano group. So let's see. If we do that one, it's 1, 2, 3. 1, 1, 2, 3, 4. The heteroatoms. So nitrogen versus oxygen. So if we count from the left, nitrogen would be on 1, oxygen would be on 4. There's not a 4-1. So that looks like the best answer.
Yeah. So those ones you just got from oxygen to the nitrogen.
That wouldn't make any sense. I mean, if we said Right, it's a 1, 2 through 1, 6. So where's the 1? Right. Oxygen wouldn't be a 1.
Yeah, I'm in vice versa.
Yeah, we'd have to start with the carbon attached to the nitrogen.
Yeah.
So that would be on the 1 position, 2, 3, 4. Is that the longest? 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3, 4, 5. We'd have to go past the oxygen because you have to keep the functional groups together. So it would be 1 and 4. Yeah. Which set of reaction conditions, this is 34, completely removes a functional group from the target molecule and produces alkane? Uh, well, palladium is going to be a catalyst. And the only thing I know of that uses catalyst is where you have pi bonds. And you want to saturate an alkene. So B would be the best answer for that one, I think. Completely removes a functional group. So the functional group would be an alkene, leads to an alkane. But that makes sense. Which of the following functional groups would need to be protected to avoid reacting with Grignard reagent? Alcohols, definitely. That's the only one in here that makes sense. Because the Grignard reagent is what will it do? We just talked about that. Refresh my memory. Grignards. Okay. Well, I can't find it now. Because the Grignard carbon is going to be negative, isn't it? Yeah. So the Grignard is going to be negative. What would it do? Extract a proton? Yeah, that's the only thing that makes sense. So it's a Lewis. So electron donor. Lewis base. It would be a Lewis base, Grignard reagent. Choose a selective reagent that will form the intended product. All right, so we got 1, 2, 3, 1, 2, 3. We're not changing the carbon chain. This is an elimination reaction. So is it an E1 or an E2? The bromine going to leave first? No. What we need to do is deprotonate. That seems to be when we have a 2 or more step process, a lot of times deprotonation or protonation, either one, is the first thing that happens. So if we use this tertiary butyl alcohol and tertiary butoxide anion, then it would deprotonate the terminal methyl. It's a strong base. So it'll take a methyl off of that end. And we got a bromine here. So this is going to be the phenyl group. And what's going to happen is that tertiary butoxide is going to come in here. And this is a carbon with hydrogen on it, I think. Okay. It's going to deprotonate it. And the electrons here are going to go there, like that. This has to go there like that. So that would be an E2. See, I only use 3 arrows, so I'm safe.
Yeah.
What's the relative position of the heteroatoms? This one. Okay. Well, in this case, we count from the phenyl group out, I think. 2, 5, 6, yeah. So they're in a position of, you know what? When we talk about relative positions, we're not strictly confining ourselves to the nomenclature convention. We do when we can. And in this case, we use the smallest numbers available. Which one is 1? Well, the carbonyl could be 1, and then the hydroxyl could be 3. Or the hydroxyl could be 1, and the carbonyl could be 3. They're still in a 1-3 arrangement. We're about done.